Today we also discuss one important theorem related to algebra. Okay, we also known about that relatively prime polynomials. Okay, then we also discuss this related theorem. Relatively prime polynomial means this one f1x, f2x are relatively prime polynomial means these have f1x and f2x. These two polynomials have no common positive factor, no common positive factor. Okay, no common factor. Okay, no common factor or or no common positive polynomial. Okay, positive degree polynomial. Okay, no common positive degree polynomial divide f1x and f2x both. Okay, then this polynomial is called relatively prime polynomial. Okay, so f1x and f2x have no common factor or no common positive degree polynomial divide f1x and f2x both. Okay, so we erase that portion and going to further discussion of that. This one, if this condition satisfies, that means f1x and f2x are relatively prime polynomial, then there exist polynomials q1x, q2x such that q1x, f1x plus q2x, f2x equal to 1, where 1 denote the constant polynomial with value 1. Okay, so we're going to prove of that. Okay, now we start with this portion. Here we write proof. Now without loss of generality, okay, we considered, assume that the degree of f1x, the degree of f1x is greater than or equal to, is greater than or equal to the degree of f2x, the degree of f2x. Okay, so we considered f1 or f2 arbitrarily. So if we change that means this one, that means in place of f1 we write f2, in place of f2 we write f1, then not a problem at all. So we write here without loss of generality. So without loss of generality we assume this one, degree of f1 obviously greater than or equal to degree of f2. Okay, then the proof is done by, the proof is by mathematical induction, okay, on the degree of f2x, on the degree of f2x. Okay, then what happened, we write it here, if f2x, if f2x has degree 0, f2x has degree 0, then f2x is a, then f2x is a non-zero constant c. Okay, non-zero constant c. Okay, then in this case we considered q1x equal to here 0 and q2x equal to 1 by c. Okay, then what happened? Then we erase our portion and going to further discussion of that. Okay, now suppose that now suppose that okay now suppose that the theorem holds whenever the polynomial of lesser degree has degree less than n. Now suppose that the theorem hold, okay, because we considered the mathematical induction on the polynomial of lesser degree. Okay, so we considered that the theorem holds whenever the polynomial of lesser degree, okay, has degree less than n, has degree less than n for some positive integer n, for some positive integer n. Okay, and suppose that, and now suppose that this one hold, suppose that f2x has degree n. Okay, f2x has degree n. That means if f2x has degree less than n, then obviously that means we find q1x and q2x such that q1x f1x plus q2x f2x equal to 1. Okay, if f1x and f2x are relatively 5. Now we're going to be prove that if degree 8, then what happen? Okay, so by division algorithm, there exists polynomial qx, and rx, okay, such that rx has degree less than n. Okay, degree less than n. And what happened? And f1x equal to this one qx f2x plus rx. Okay, this one we marked as star. Okay, then we're going to discussion of that since f1x and f2x are relatively prime, okay, then rx is not the zero polynomial, then rx is not the zero polynomial. Okay, now we claim that what we claim that f2x and rx f2x and rx are relatively prime, are relatively prime. Okay, then what happened? Then we write suppose otherwise, that means this one is not happen. Suppose otherwise, okay, suppose otherwise, then there exists a gx of positive degree. There exists a gx of positive degree, okay, obviously that divides both, that divides what, f2x and rx, okay. If this one is not happen, then this one happen, okay. Then what is need for that? We erase that portion and going to further discussion of that. Hence by 5, hence by this one star, we mark as star, gx also divide, okay, f1x, and contradicting the fact that if that means if some polynomial divide f2x and rx, then obviously this polynomial divide f1x. Then contradicting the fact that gx divides both, okay, divides both f1x and f2x. This can't be possible, okay. So what happened? That means, sorry, cannot we write here some mistake, okay. This implies that this one, this implies that, okay, this one gx divides both. Then we write contradicting the fact that f1x and f2x are relatively prime, okay. So what happened? So our assumption, this assumption, that means this implies that f2x and rx are relatively prime, and obviously rx have degree less than n, if n equal to what, degree of f2x. So what we do here, we do, that means by our assumption, what, this satisfies this, that means given condition. So we write it here, that means we imply induction hypothesis, we apply here induction hypothesis, okay, for f2x and rx, okay. Then what happened? Then obviously there exist polynomials, okay, there exist polynomials, what, g1x and rx, okay, sorry, g1x and g2x, okay, such that what, such that this one, we erase our portion and going to further discussion of that. This one equal to what, g1x f2x plus g2x rx equal to 1. Now we put, rx, okay, that means we put the value of rx, okay, from what, from star, okay, we get what, we get g1x f2x plus g2x, here rx equal to what, rx equal to f1x difference qx f2x, okay, equal to 1. This implies that g2x f1x plus g1x difference g2x qx f2x equal to 1, okay. Then we erase that portion, or erase lower portion, and going to further discussion of that. We talk about that what, this one equal to q1x, here f1x, and this one equal to f2x q2x equal to 1, where q1x equal to g2x and q2x equal to g1x difference g2x qx. Understood? I think all are understood that portion too easily, because we do step by step manner and obtain our concluding result, okay, or required result. So we get this one for the degree of lesser polynomial f2x equal to n, and we assume that the degree of lesser polynomial less than n, this, that means this given, that means required, given condition of required result is hold, okay. That then what happened, that means by mathematical induction, this one is true for all in, okay, by mathematical induction this results valid for for any polynomial of degree of finite degree, okay, of finite degree. So we do our required result, okay. So we prove this important theorem, which theorem says about that if two polynomials are relatively prime, then we find another two polynomial whose that means obviously linear combinations of relatively prime polynomials, okay, where coefficients are obviously polynomial. Then we find this linear combinations of these two polynomial equal to 1, okay. Obviously this one is constant polynomial. So this one important result. We now going to further discussion of one example related to this important theorem, okay. Understood or not? We write here example. We start it now. Let f1 x equal to here x cube difference x square plus 1. Okay, here we write it in better way. That means we talk it in better way. X to the power cube, x to the power, okay, that means x to the power 2, x to the power 3 plus 1. Okay, and f2x equal to x difference 1 whole square. Then what happened? Then obviously these two are f1x and f2x are relatively prime. Okay, relatively prime. Then what happened? Then we talk about that q1x equal to minus x plus 2 and q2x equal to x square difference x difference 1. Okay, then what happened? Then q1x f1x plus q2x f2x equal to 1. Okay, then we also talk about that. That means if we construct any relatively polynomial, then we find two polynomial satisfies these conditions. Okay, so that means this one just simple example. If we're interested about that, then we also take another simple example. Okay, simple f1x equal to x difference 1 and f2x equal to here x square, okay, difference 2, f1x f2x. Then what happened? Then this one are relatively prime polynomial, yes or no? Yes. Then we find some q1 and some q2. We write it q1x equal to what and q2x equal to what. Okay, then we find q1x f1x plus q2x f2x, okay, equal to 1. If we do it in, that means if we write here x, then here what happened? Here is, that means x square difference x. Okay, x square difference x, and if we write q2x equal to 1, then what happened? Then that means then we erase that portion and match this one here difference x. Okay, that means x square, okay, plus, if we write plus 2, then what happened? Here x square difference x plus this one, that means we write wrong this one. Okay, then x square plus x square minus x plus here 1. Okay, plus not 2 plus 1. Then we do this one. That means we create another example. This example satisfies our this relation. Okay, understood or not? Just f1x equal to minus x plus 1 and f2x equal to x square minus x plus 1. This one are obviously, that means relatively prime polynomial. Then we find q1x equal to x and q2x equal to 1 and satisfies this that means result. Okay, q1x f1x plus q2x f2x equal to 1. Okay, not a problem at all. All understand this. That means example. Obviously, we also discuss two examples and relative, that means theorem, and relatively prime polynomial we also discussed today. So if you get this type of videos, please subscribe my channel. If you give like, please click on like option, and if you have any comment, any suggestion, any questions, write it in comment box. So today I stop here. Thank you.